Okay, so welcome to this next video in which we're discussing endocytosis. Okay, so at the moment what we've done is we've looked at an overview of endocytosis, we've then looked at endocytic motifs, and now what we want to do is look at some experimental history as to how we discovered endocytic motifs. Okay, so this wasn't actually done in neurons at all. Instead, the endocytic motifs were discovered by Brown and Goldstein, who were looking at a very different sort of endocytosis. So Brown and Goldstein were interested in familial hypercholesterolemia. So Brown and Goldstein. Okay, so they were looking at people who had an inherited condition which meant that the blood LDL concentration was far too high, and therefore there was far too much cholesterol in their blood because the LDL particles have cholesterol within them. Okay, right. So what they found is that people with familial hypercholesterolemia, which is often abbreviated to FH, so I'll write this out in full. So FH stands for familial, which just means that it runs in the family, hypercholesterolemia, which means that you have too high cholesterol level within the blood, hypercholesterolemia. Okay, right, hypercholesterolemia. So they were looking at people with familial hypercholesterolemia, and what they found is that they had a mutation in the gene that coded for the Ldl receptor. So let me show you the structure of the Ldl receptor. Okay, so this is obviously just a cartoon here, but basically it has a large extracellular domain. So this is the extracellular fluid here, and this is the cytoplasm here, cytoplasm. Okay, and this is the Ldl receptor. Okay, right. So let me explain to you what LDL is, and then I'll explain to you what the LDL receptor is going to do. So, LDL stands for low-density lipoprotein. Low-density lipoprotein. Okay, and basically they are small balls, okay, of lipid particles. Okay, so basically, if you want to transport lipid molecules around the blood, around the body, then you can't just put them into the blood. The reason being that they are not soluble. So what you'll get is you'll get the fat molecules separating out from the blood plasma, and that won't be good at all, basically. So instead what you do is the way that you transport lipid molecules around the blood is in these lipoprotein particles. So what is a lipoprotein particle? Well, basically it's many phospholipids all wrapped around in a ball. So it's a little ball, okay, of lipids. And if we remind ourselves of the structure of phospholipids, so the structure of a phospholipid is that you have two long-chain hydrophobic tails, okay, or long-chain carboxylic acids, and then you have a phosphate head here. So this little circle here represents the phosphate head of the phospholipid. So this is the phosphate head of our phospholipid here, okay. And the phosphate head has a negative charge, so it's polar. It interacts with water quite well. Okay. Now the backbone of the phospholipid is this line here, which I've put in green. This is the glycerol molecule. So in green here, this is glycerol. Now the full chemist's name for glycerol is that it's propane 1,2,3-triol. So glycerol is more properly known as propane 1,2,3-triol. Okay, and although propane 1,2,3-triol is a bit of a mouthful, it's useful because it tells you exactly what glycerol actually is. It's this free carbon molecule, propane, where every single one of the carbons has an alcohol group off, so 1,2,3-triol. So with 3 alcohol groups in total, one off each of those 3 carbons. Now, to this third carbon here, which has an alcohol group off, you esterify a phosphate group to that third carbon via a phosphate ester bond. Okay, and then to the first two carbons, hydroxyl groups, you instead esterify carboxylic acids, so long-chain carboxylic acids as they're called, or free fatty acids. These are fatty acids that you've esterified onto the first and second hydroxyl groups of the glycerol molecule. And again, the proper chemist name for a fatty acid is that it's a long-chain carboxylic acid. Okay, carboxylic acid. Right, so what happens is that when, well, basically this whole structure now is a phospholipid. Okay, and what you do is you can put loads of these phospholipids around, like so, in a circular arrangement. So here's another one here. And you can have all of the hydrophobic tails, which are the portions which don't interact well at all with water, and what makes these phospholipids insoluble. You can put all of those facing the center, and you can put the phosphate heads facing the outside, basically. So here are the phosphate heads. So let me draw one more here. Okay, so you can have the phosphate heads around the outside of this particle that we're producing here. And then you can have the long-chain carboxylic acids, which are esterified to your glycerol molecule, and are being shown here in orange. They can all face into the center of this particle, like so. And they all interact very nicely with each other because they're all big hydrophobic molecules. So they all interact nicely with each other. And then around the outside, you then have these phosphate groups of the phospholipids facing out towards the blood plasma, okay? And these heads of the phospholipids are polar. These phosphate groups are polar, so they can interact nicely with water. Okay, and we'll continue this discussion in the next video.